So in today's talk, we'll be covering a variety of cycloadditions. The first one will be centered on the Diels-Alder reaction, and that involves the bimolecular association of a diene combining with a dienophile, and this is classed a 4+2 cycloaddition. So you have 4 pi electrons here, 2 pi electrons here. They combine to form a 6-membered cycloadduct. These reactions are particularly interesting when your reactants are substituted, and these transformations typically go with a high degree of regioselectivity and stereoselectivity. So they're interesting synthetically, and they're very, very popular, well-studied reactions. The mechanism is shown here. So this is a paracyclic reaction where the pi electrons are flowing in a cyclic fashion. It's not entirely clear what is attacking what. You can imagine that the diene, here is attacking the dienophile. You have a back attack, and then this double bond rearranges to form a double bond here. That is also shown in the adduct here. Or you can also view it as the dienophile attacking the diene, and that will really become important later on in the talk, as I will point out. So typically when you want to study a reaction using computational chemistry, you're going to go ahead and locate, using DFT or other methods, the structure and energy of your reactants. You'll do the same for your products, and then via some interpolation or potential energy surface scan, you can find the transition state that really links these two stationary points. And for the Diels-Alder reaction, here you have the reactants that I've shown you. Here you have the optimized structure of the diene, the dienophile, and your adduct here, your 6-membered ring. And the activation strain model, it posits that the activation barrier is equal to the sum of the strain energy and the interaction energy. And let's go ahead and visualize what that really means. So your strain energy, by definition, is the energy difference between your distorted reactants and your pristine reactants before they've come together to react. And in this particular transformation, you have the terminal carbons that are reacting. In the reactants, they're sp2 hybridized, they're nicely planar. But over the course of the reaction, they begin to pyramidalize. The same thing happens for your dienophile. It too becomes pyramidalized. And all of these all of these geometrical differences, they manifest in a destabilizing strain energy. So that's why the strain energy is more or less an energetic penalty to adopt the transition state geometry. But simultaneously, these distorted reactants, they do favorably interact, and that's a counteraction to the destabilization, and this is a favorable interaction. So that's the activation strain model. So it's the sum of the strain plus the interaction energy, which is stabilizing, and that is the physical manifestation of the activation barrier. What is interesting is when you project your energy along a reaction coordinate, so not just at the transition states alone, but along every single point along your IRC. And then you have 2 reactions. One is the black reaction here, and one is the red reaction. It doesn't matter what the reaction is, but we can all see that the black reaction has a kinetic preference, right? The activation barrier is lower, the transition state's lower here, and it's also thermodynamically favored here. So it's one thing to find these reaction paths. It's one thing to say, okay, the black reaction is faster, but then it really becomes interesting to understand why the black reaction is faster. So we can go ahead and plot the strain energy and the interaction energy along this reaction coordinate. And in this example, you see that the strain curves, the black and red curves, are pretty much superimposed. So one can argue that the black reaction is faster, not because of differences in the strain energy, because these curves are on top of each other, but instead the black reaction is faster because it benefits from a more stabilizing interaction energy along the entire reaction coordinate. And that has two effects. First of all, more stabilizing interaction. It pulls the transition state lower. So the black transition state is lower in energy, and it also pulls it to an earlier point on your reaction coordinate. So we can see that this would be an earlier transition state, typically with longer inner atomic distances. This is all in accordance with the Hammond postulate. Okay, so I would argue that analysis at a consistent geometry would give the most insight into the factors controlling reactivity, and that is what we will do in this talk later on. So we're going to pick a point on our reaction coordinate with a consistent carbon-carbon forming bond distance and do our analysis there. And I want to point out that analysis at the transition state could possibly be misleading. So in this scenario, if you were to do the activation strain analysis at the dots, so at this transition state and at this transition state, you would erroneously conclude that the black reaction is faster because of a less destabilizing strain energy. When in reality, if you project this along the entire reaction path from reactants to transition states to the products, then you see it really is the more stabilizing interaction energy that is the crucial factor for the lower, more favorable, and faster transition state for the black reaction. Okay, so this is a very nice, say, overview of reactivity, the factors controlling reactivity, and this method can be applied to study any reaction, whether it's organic, inorganic, catalytic reaction, biological reactions. So it's a really, really robust tool. And so when the interaction energy is important, we like to turn to the energy decomposition analysis tool in ADF. And this tool allows us to decompose this interaction energy into what I would argue are really physically meaningful energy terms that I can wrap my head around. So the first such term is your electrostatic interaction, and that's going to encompass the stabilizing Coulombic interactions between, say, the electrons on one fragment and your nuclei on the other. You also have the reverse, and then it also encompasses the destabilizing electrostatic interactions, say, between your nuclei on one fragment and your nuclei on the other, and analogously your electrons on one fragment and your electrons on the other. And then you have your Pauli repulsion. This is your 4-electron, 2-center repulsion. That is the physical manifestation of the steric repulsion. And that's going to be proportional to the overlap squared of your filled orbitals. So the more your filled orbitals are overlapped, the higher your Pauli repulsion will be, because the electrons of the same spin do not want to occupy the same region in space. The third term is your orbital interaction term, and that mainly encompasses your donor-acceptor interactions, such as your HOMO-LUMO interactions, in addition to polarization. Okay, and the orbital interaction term is going to be proportional to the overlap squared divided by now the energy gap between the orbitals. So a smaller HOMO-LUMO gap means a smaller delta epsilon, and thus a larger orbital interaction. And in addition, the more those filled and unfilled orbitals overlap, also the greater the orbital interaction will be. So that's really the biggest difference between your Pauli repulsion and your orbital interactions, is one's proportional just to the overlap squared and the other is proportional to the overlap squared divided by the energy gap. Okay, in addition, if you employ an explicit dispersion correction such as GRIMAs, D3 or D4, with or without damping, then you will get a fourth energy term in your energy decomposition analysis. Okay, so some computational details. So all calculations were performed with ADF, and the geometry optimizations were performed using a GGA functional, specifically the BP86 functional, in conjunction with a triple zeta quality basis set. And so we've taken care to benchmark this computational method, and we know it performs really well. And depending on the situation, we either do or do not include an explicit dispersion correction. So this would be the GRIMA D3 with the Becky-Johnson damping functions here. We use Zora to account for relativistic effects. And I also find it important to check that the trends in reactivity are consistent in solution, for example. And in these cases, we've checked that our gas phase chemistry provides energetic trends that are consistent when you model implicit solvation using Cosmo. This is also natively in ADF. And we've also tested that our trends in reactivity are the same when we compute it with hybrid functionals or meta-hybrid functionals, with or without dispersion. A little bit about our benchmark study. So this was published in PCCP about 2 years ago. So we studied a range of paracyclic reactions, of Diels-Alder reactions, 1,3 dipolar cycloadditions, electrocyclic reactions, sigmatropic rearrangements, and double group transfers. So we've optimized all of our stationary points using CCSD parentheses T with a very large Dunning basis set. We've obtained our final energies using a focal point analysis where we can nicely see how all of our energies converge with regards to Coulomb correlation. For example, moving from Hartree-Fock to MP2 to CCSD, so on and so forth, all the way out to perturbative quadruples here, in conjunction also with a hierarchical series in basis sets. So we, like I mentioned, run with the Dunning basis sets here. Okay, so I would argue that this approach to a benchmark is preferable compared to a single shot benchmark where one just employs CCSD parentheses T with a a small basis set. Using that approach, you don't know how good your energies are converged, but ours are converged within a few kcal. So we're really confident that we have the most accurate benchmark for paracyclic reactions. But now to the chemistry. So we're going to begin with understanding how Lewis acids catalyze Diels-Alder reactions. The work was performed by Pascal Vermeer and was published a few years ago. So here is the Diels-Alder reaction between isoprene and a alpha-beta unsaturated methyl ester. The uncatalyzed reaction at room temperature takes about 70 days, so it's very sluggish. It gives quantitative conversion to a mixture of these regioisomers. So this is a 1,3, say, adduct, and this is your 1,4 adduct. So it gives 30% this, 70% this. It's very nice to see if you add a Lewis acid, so aluminum trichloride, it will coordinate to the oxygen of your dienophile. And at room temperature, so the same temperature as this, you get quantitative conversion in 3 hours. And it's mostly regioselective to afford the 1,4 adduct. So it's clear Lewis acid. The Lewis acid can not only speed up the reaction, but it can also make it largely regioselective. Very interesting. So we sought out to first, we sought out to understand what is the origin of this effect of the Lewis acid. So we jumped into the seminal work in JAX published by Hauk, and yeah, it's always nice to check the textbooks. So Lewis acids, it is common believed that Lewis acids reduce the HOMO-LUMO gap, and more or less they consider these reactions to be purely normal electron demand interactions, where the highest occupied molecular orbital of the diene, here it is, it has 2 electrons, the highest occupied molecular orbital will donate charge into the lowest unoccupied molecular orbital of your dienophile. So this is, say, the uncatalyzed situation. Now, if you put in your Lewis acid, it will coordinate to the dienophile and stabilize that lowest unoccupied molecular orbital. And we all remember from a few slides before, it's the HOMO-LUMO gap. So now you have a smaller HOMO-LUMO gap, and that should in fact lead to stronger orbital interactions, a more stabilizing interaction, and thus a lower barrier. So that is the established, say, rationale. So we wanted to, check what's actually going on. So we decided to run with this Diels-Alder reaction isoprene with our, say, alpha-beta unsaturated methyl ester. And we wanted to study the effect of various Lewis acids. So we started with the uncatalyzed reaction just to have a baseline. And then iodine is a weak Lewis acid that's nowadays gaining a lot of popularity in catalyzing reactions, and some intermediate strength Lewis acids, and also a very strong aluminum trichloride Lewis acid. So the first thing we wanted to study was just the basic interaction between a Lewis acid and our dienophile. And so this, the activation train and the EDA method it's a fragment-based approach. And in this case, it's very clear what our fragmentation is. It's going to be the Lewis acid is one fragment, and then our substrate is the other fragment. And I've arranged the Lewis acids in strength of in order of their strength. And here you see the interaction energy. It's negative, so this complexation is stabilizing. And you see the number gets more and more stabilizing as we move from a weak Lewis acid to a strong Lewis acid. Now let's go ahead and do this decomposition scheme. So we can, before we get there, I wanted to say something about the relative Lewis acidity measured by really nice NMR experiments. And the trend in interaction energy nicely mirrors the trend in experimentally determined relative Lewis acidity. So that's always nice to have an experimental validation of your computational prediction. Okay, let's use our EDA method to decompose our interaction energy now. And here we see that the electrostatic interaction becomes more stabilizing along the series. Okay, that's nice. The Pauli repulsion becomes more destabilizing. So this is a positive energy. This is unfavorable. But importantly, we have a decent amount of a covalent character of this interaction here. So this is our orbital interactions. These are all negative, and they become increasingly negative from our weak to strong Lewis acid. And that'll become very important later on. So try and keep that in mind. We're going to come back to that. And just for fun, I wanted to plot the energy of the lowest unoccupied molecular orbital of the overall complex. And this was interesting because there really does not appear to be a systematic trend here. So here's the energy of the LUMO. Okay, it goes down, and then it goes down a little more, but then it goes back up, even though zinc dichloride is a stronger Lewis acid than titanium tetrachloride. And so it's just not very systematic, and could be the first indication that the LUMO lowering effect is maybe not the full story. Okay, so here we have our activation strain diagram. On the y-axis, we have our total electronic energy, and on the x-axis, we have our reaction coordinate. And in these reactions, we're going to be projecting all of the energies on the distance between the newly forming carbon-carbon bond, and we pick the shortest of the two newly forming carbon-carbon bonds. Okay. And in black, we have the uncatalyzed reaction. And in red, we have the reaction catalyzed by aluminum trichloride. And this is a strong Lewis acid, and it makes sense that the barrier would be much lower, right? So this is our catalysis here. And now let's go ahead and figure out why is the red reaction lower, okay? So it's lower in part because it benefits from a less destabilizing strain energy around the transition state region, right? This is lower than this. When you look at the transition state structures, then you see here we have the uncatalyzed reaction. Here you have the newly forming carbon-carbon bond distances. And here you have the difference between these newly forming distances here. And that difference amounts to 0.46 angstrom. And in the case of the Lewis acid catalyzed reaction, the path becomes even more asynchronous. Now the difference in the newly forming bonds is much larger. And so we've already established that the strain energy for these reactions can be traced back to, the structural reorganization of your fragments. And here we see now one side is reacting, the other side is much less reacted, right? The difference is much larger here. So this carbon is not super parameterized yet, neither is this carbon. So that's where you really get a benefit. So a more asynchronous reaction path typically leads to a less destabilizing strain energy. So these sorts of insights really encouraged us to dive into the origin of asynchronicity in Diels-Alder reactions. So if you're interested in such a topic, I would refer you to this PCCP paper of 2021. But I would argue that the red reaction is really faster because it benefits from a more stabilizing interaction energy along the entire reaction coordinate, right? So here's the interaction energy for the catalyzed reaction. Here it is for the uncatalyzed reaction. So that really prompted us to decompose our interaction energy using our ETA method. So this is the same data. It's only plotted on a different y-axis, so it looks a little different here. And now we decompose it into the orbital interactions. And this was very surprising to us at first, because if the Luma lowering effect was really operative, then I would have expected the red curve to really be more stabilizing along the entire reaction coordinate. And in the transition state region, the trend is actually opposite. So the orbital interactions are not really key here for explaining catalysis, and neither is the electrostatic interactions. So we actually see that the uncatalyzed reaction benefits from a more stabilizing electrostatic curve here, and it's the Pauli repulsion that is really operative here, and the catalyzed reaction benefits from a less destabilizing Pauli repulsion along the entire reaction coordinate. So it's really the repulsion between the two reactants that is operative in governing a more stabilizing interaction and thus a lower activation barrier. So we wanted to dig into the origin of the Pauli repulsion, and you may remember me of mentioning that it's related back to the overlap of filled orbitals. Okay, so we analyzed all of the overlaps between the two fragments. That is, on one side you have the diene, on the other you have the dienophile, and we found that it can be traced back to the overlap of the HOMO-1 on our diene, which is the all-in-phase pi orbital here that you see of the diene. It can be related back to that, overlapping with the pi molecular orbital on the dienophile. And for the uncatalyzed reaction, that overlap amounts to 0.13. That is quite large. And then when you add your Lewis acid, that overlap decreases a lot. And that is the origin of the less destabilizing Pauli repulsion. Let's go ahead and visualize these molecular orbitals. So the diene, this is the HOMO-1, the all-in-phase pi system. Here you have the uncatalyzed say reaction. This is your dienophile. Here you see quite a large lobe here. This is the pi bond that's reacting with your diene. And upon coordination of your Lewis acid, you have charge transfer from your substrate to the Lewis acid. Here you see electron density here, and that substantially reduces the MO coefficients of the carbon 2pz orbitals here. You see they're much smaller than they are here. So this overlaps a lot less with the HOMO-1 of your diene. And that less overlap leads to less repulsion and thus a faster reaction. Then we wanted to understand, why is there no difference in orbital interactions, right? So as one would expect here, you have the normal electron demand. That's going to be the donation of charge from your HOMO of your diene into the LUMO of the dienophile. That is exactly what textbooks would say and what we expected initially to be happening. So the HOMO-LUMO gap for the uncatalyzed reaction is 2.3 electron volts. The orbital overlap is 0.2. Okay, when you add your Lewis acid, the gap gets smaller. Okay, that's exactly what we would expect. And the overlap, okay, gets a little worse. But the interesting thing is that these reactions are both in normal electron demand and inverse electron demand. There's typically always these two that are happening, right? So the Lewis acid, it not only stabilizes the LUMO, so it pulls the LUMO down, but it also stabilizes the pi molecular orbital here that that would be involved in the inverse electron demand interaction. So here you have the the LUMO pi MO gap for the uncatalyzed reactions, 4.6. Here's the overlap with the Lewis acid. Now your energy gap is much larger. The overlap is also worse. So while strengthening the normal electron demand interaction, you weaken the inverse electron demand interaction by means of the Lewis acid. So the first conclusion would be that Lewis acids catalyze. Lewis acid catalysis goes with a novel Pauli lowering catalysis mechanism. It's not caused by an effective enhancement of the Lewis acidity of the dienophile, but instead due to polarization of the pi system away from the carbon-carbon bond, which reduces the 4-electron Pauli repulsion with the diene. We saw that leads to a less destabilizing Pauli repulsion. And that effectively stabilizes the overall diene-dienophile interaction. So you have a more stabilizing interaction. And that ultimately is the cause of the lower activation barrier, our lower delta E. So at first we wondered, is this really just specific to this Lewis acid catalyzed Diels-Alder reaction? And it is indeed quite a general phenomenon. So this whole saga started with understanding how dihalogens catalyze Michael additions. And that's also Pauli-Laurent catalysis. Here you saw the paper I just discussed. We've studied, say, aminium catalyzed Diels-Alder reactions, aromatic 4+2 cycloadditions, bifunctional hydrogen bond catalyzed reactions, so on and so forth. So really a diverse range of cycloaddition reactions are governed by this mode of catalysis. So we would argue it's a quite broad phenomena and something to be aware of. A few years back, we also summarized our findings in an account as part of the ACS. The second paper I would like to discuss is the work was carried out by Evelyn T. Kink and also by Pascal Vermeer. And here we want to understand the cycloaddition reactivity of a molecule called tropone. So looking at it at first glance, I would argue that it's a relatively simple organic molecule, right? So you have one oxygen atom, a few carbon atoms. Of course, there's hydrogens around, and it's in a cyclic form. So at first glance, quite a simple organic molecule. but it has a ton of potential to be a very useful reactant in a diverse range of cycloadditions. So over the years, it's been showcased to engage alkenes in 4+2 cycloadditions. It can engage cyclopropanes in 6+3 in higher order cycloadditions, also alkenes and dienes in 6+4 cycloadditions. And it can also engage, it can employ all 8 pi electrons in these higher order 8+3 and 8+2 cycloadditions. So despite its potential to engage, a variety of reactive compounds in higher order cycloadditions, it really exhibits a low reactivity. So there are 2 ways that one can tempt tropone to react, and one is by Lewis acid catalysis, and this has a really stable highest occupied molecular orbital. It has a very stabilized LUMO. So these reactions are really driven by inverse electron-demand interactions, IED, where the electron flow is going to start at the ethylene or at the dienophile, and it's going to go into the LUMO of your tropone. So you can enhance this inverse electron-demand interaction through coordination of Lewis acid, which stabilizes the pi LUMO and thus leads to a smaller HOMO-LUMO gap. Or you can envisage tempting tropone via Umpelung chemistry, where you invert the charge. So a normal carbonyl is going to have a delta positive carbonyl carbon and a delta negative carbonyl oxygen, and through Umpelung chemistry, that's what I depict here. Through Umpelung chemistry, you can invert this charge. So you can push charge into the ring, thereby making the carbonyl carbon delta negative. That's what you see here. And that would, think about that. So if you push charge in, you're going to be destabilizing your pi HOMO via, say, antiaromaticity, for example. So this is aromatic. If you're pushing charge in, then you're going to have, say, 8 pi electrons here. Okay, so Umpelung strategy would destabilize the pi HOMO, and that too would lead to a smaller HOMO-LUMO gap, and thus, more stabilizing orbital interactions, more stabilizing interaction, and thus a lower barrier. So we studied out to we studied this reaction of this dimethoxy substituted ethylene reacting with our tropone, and we studied various Lewis acids, and we modeled both the Diels-Alder reaction, the 4+2 cycloaddition, or the 8+2 cycloaddition here. Here you see the 4 pi electrons involved in the Diels-Alder reaction, and here now you have the 8 pi electrons in the system here reacting the 8+2. And we were really inspired by this elegant work of Yamamoto in 2009 in this JAX paper, where they experimentally showed that you could control the regioselectivity between your 4+2 and your 8+2 adduct by the judicious selection of your Lewis acid. So with boron trifluoride etherate, you could get full 8+2 regioselectivity. With boron with triphenylborane, you too retain that regioselectivity, giving all 8+2. But the simple substitution of all 5 hydrogens for fluorine, so now you have the pentafluorophenyl version, the perfluorinated Lewis acid. Now you have complete opposite regioselectivity. Now you have exclusive 4+2 formation. And we were interested in the origin of this. First, the origin of catalysis, and also the switch in regioselectivity. So we applied our computational method here. You see Zora, BP86, D3PJ, TZ2P, okay, using ADF. And we were happy to see that we could reproduce the experimental regioselectivity. And I just want to remind everyone that getting these accurately is not a small feat. So we're talking about very small differences in your delta delta G double dagger. So we were happy to computationally see that the 8+2 was preferred with boron trifluoride. The 8+2 was also preferred for this Lewis acid, and then we saw the switch in regioselectivity here. Okay, so first we wanted to understand the origin of Lewis acid catalysis in this manifold. So here you have the uncatalyzed reaction in black, and in red you have the boron trifluoride catalyzed reaction. The transition state is definitely lower on the potential energy surface, shifted to an earlier position. We know why that is. And we apply the activation strain model once more. And here we see that the strain energy is actually more destabilizing for the Lewis acid catalyzed reaction. So that really is not, that's actually working against the trend of catalysis, right? But it's, here we have the transition states. So you see the degree of asynchronicity is already very high. And here it's really the more stabilizing interaction energy for the catalyzed reaction that pulls that transition state down and to an earlier position. So that again motivated us to do the decomposition with the EDA method with ADF. And then again, this is the same data, just again plotted on a different y-axis, and we decompose it into this electrostatic interaction. Okay, not such a big difference in these curves, so not super important. The Pauli repulsion curves are also quite superimposed, so not contributing too much to the differences here. But it was really the orbital interactions which were more stabilizing for the Catalyze. The red curve here is really below the black curve, so that's going to be really important. And this is the dispersion energy curves. You see they're relatively flat, and the differences are minimal. So the BF3 catalyzed Tropone cycloaddition really benefits from a stronger inverse electron demand interaction. So as I mentioned before, the LUMO of the Tropone is quite low. The HOMO is really, really low, and is not able to engage with the lowest unoccupied molecular orbital of the ethylene. So this is really purely an inverse electron demand cycloaddition. And here you have the energy gap. So the uncatalyzed reaction has the energy gap of 2 eV. Here you have the overlap is quite a strong overlap here. And the catalyzed reaction really benefits from a smaller energy gap here, 1.4 eV versus 2, and it actually benefits from a slightly better orbital overlap here. Okay, so the Lewis acids catalyze these cycloaddition reactions via LUMO lowering catalysis. And then we are interested in the selectivity. So here we sought to compare the triphenylborane Lewis acid catalyzed reaction with the perfluorinated Lewis acid here, the pentafluorophenyl borane. Okay, so in blue I have the triphenylborane here, and the solid line is going to be the 8+2 pathway. The dotted line is the 4+2 pathway. Okay, so we predominantly form the 8+2 energetically here and also experimentally. And here you have the solid line here. It actually leads to a lower barrier and thus a more favorable reaction. And in the dotted line, we have the 4+2 pathway, and that has a higher barrier, which is less favorable. Okay, so this is the reaction energy profile. And in green, we have the perfluorinated Lewis acid, where the regioselectivity is inverted. And in the solid line is again the 8+2, the dotted line is the 4+2. It was very interesting to see that the Lewis acid really doesn't have an effect on the 4+2 pathway for either of for these reactions, right? The 4+2 barriers are superimposed on top of each other. but it's really the difference in the Lewis acid, in the ability of the Lewis acid to catalyze the 8+2 pathway. So it really benefits the 8+2 pathway when you have the triphenylborane, and when you perfluorinate it, it slows that reaction down. And so we wanted to analyze these two 8+2 pathways, and we again turn to the activation strain model. And here we see that the origin of the more favorable pathway for the blue curve can be traced back to a less destabilizing strain energy along the entire reaction coordinate. Meanwhile, the interaction energy curves are pretty much superimposed and not really contributing to the chemistry here. So now we wanted to dig in further to the strain, and we chose this consistent geometry here. And then we did a second decomposition. So here we have the Lewis acid coordinated to the tropone, and here you have the dimethoxyethylene, right? And just keep in mind that the dimethoxy, it is in close proximity to the Lewis acid. That'll become important later on. Much more so than when it's reacting in the 4+2 reaction manifold. Okay, but here you have the strain energies for the triphenylborane and for the perfluorinated version. You see the strain energy is higher. It's more destabilizing for the fluorinated version here. And that can be traced back predominantly to the strain of the Lewis acid tropone fragment. So this fragment here in red, because the strain of the ethylene fragment is the same, 9 kcal. So why is this strain energy more destabilizing here for the fluorinated Lewis acid? We then did a second decomposition. Now our fragments are the Lewis acid interacting with the tropone. And here you see that the strain of the tropone, while it being destabilizing, right, it doesn't change very much. But really, it's the strain of the Lewis acid that's way more destabilizing. It's 6 kcal versus 3 kcal. So it's really more destabilizing for the perfluorinated Lewis acid. And so over the course of this reaction, the 8+2 pathway, the substituted ethylene, it really sterically clashes with the Lewis acid. Right? The two methoxy groups are even oriented towards the Lewis acid, and this is really the lowest energy conformation for this process. So there's substantial steric clash between the incoming substituted ethylene and your Lewis acid, and so we were able to find out that the origin of the differing regioselectivity between the triphenylborane and the perfluorinated version, it arises from the ability of the Lewis acid catalyst to facilitate the buildup of differing degrees of geometrical deformation. So the steric clash between the reactants causes the Lewis acid to deform heavily during the 8+2 pathway. We saw that on the previous slide. And this deformation requires less energy for the triphenylborane compared to the perfluorinated Lewis acid. And that can be traced back to the strength of the boron phenyl bonds. So the boron carbon bonds that link to the phenyl group here. So this BC bond is much weaker than the BC bond in the perfluorinated version, and it's much easier to bend and deform weak bonds than it is strong bonds. So the lower 8+2 cycloaddition barrier for this Lewis acid is because it's easier to deform this Lewis acid compared to the fluorinated version. So you can really control the regioselectivity. So this Lewis acid gives 8+2, whereas the perfluorinated version gives exclusively 4+2. Now, to the third and final story today is going to be about how not antiaromaticity gain, but increased asynchronicity enhances the Diels-Alder reaction of tropone. Work was again carried out by the same team as before. So earlier on in the talk, I discussed a different strategy to enhance or tempt tropone to react, and that was via Umplong chemistry here. So this was a reaction studied by the group of Wu and Alabugan in 2020. And they studied the reaction of a malamide here. This would be your dienophile, and the tropone would be your diene. And they showed how this reaction does not proceed. And that was attributed to the low HOMO energy because this molecule is aromatic. So they thought, they considered what happens if you were to place a negative point charge on the outside of this molecule. A negative point charge would then induce Umplong chemistry, where you invert the charge of your carbonyl. You would push charge into the ring and thus induce antiaromaticity. And they coined this HOMO activation. They proposed a more realistic way of doing this by installing a functional group that would carry a negative charge that you see here. And then say this is more experimentally say feasible here. And this would also, so here's your negative charge in analogous way to here. And this would also induce Umplong and HOMO activation, induce antiaromaticity, all that good stuff. So I completely agree that these would be strategies to get tropone to react. Okay, they measured the nucleus-independent chemical shift at 1 angstrom above the center of the ring. They did that for tropone. They showed that it's negative, so it's aromatic. They measured the highest occupied molecular orbital. That orbital is, as I mentioned, it's very stable, and it's negative 8.7 electron volts. They did the same analysis now for this for the hydrazone ion. They measured the Nix. Now it's extremely positive. So from a magnetic standpoint of aromaticity, this would indicate strong anti-aromaticity here. And that is also in line with the much less stable highest occupied molecular orbital. So in tropone, it was minus 8.7, and now in this, it's only minus 1.4. So this is what they attributed the enhanced reactivity of this molecule to, just the HOMO activation. Okay, so we wanted to see this reaction. And then we modeled the uncatalyzed reaction here in black. So that would just be, say the pristine tropone reacting with our malamide. Here you see a barrier of 21 kcal, very high. And then in red, we have our hydrazone anion, and that benefits from a submerged transition state. It actually forms a stable reacting complex here, and then it has a barrier of minus 8 kcal. We'll decompose the barriers into the strain energy. So around the transition state region, you see that the hydrazone reaction really benefits from a less destabilizing strain energy, right? The strain energy for the tropone reaction is much higher, much more destabilized. But really, the hydrazone reaction benefits from a more stabilizing interaction energy along the entire reaction coordinates. And we wanted to understand the trend in strain energy. So here you have again, you have the degree of asynchronicity here. So here you have the difference between the two newly forming carbon-carbon bonds that amounts to 0.16 angstrom. That's just the difference between this and this. And this is for tropone. This is for the hydrazone. Now it's extremely asynchronous. And the difference is 1.22 angstrom. So you see this carbon-carbon bond is way longer than this one. So that is what leads to the less destabilizing strain energy for this molecule. That's why you see the curve, the red curve in the transition state region is much less destabilized here. Now we wanted to understand the interaction energy. So we decompose that into the electrostatic curves. That shows that there is some electrostatic interactions that are more stabilizing for the hydrazone, but it's really the Pauli repulsion, and it's really the hydrazone goes with the less destabilizing Pauli. The orbital interactions, interestingly, are not contributing to the faster reaction for the red curve. Around the transition state, they're actually the same. And the dispersion curves, not too much to see here. They're flat and overlapping. Okay, so first things first, we want to understand the origin of the Pauli repulsion, since that is really decisive in determining the enhanced reactivity. So here we were able to quantify the overlap of a key pi molecular orbital of the diene with the pi HOMO of the malamide. And we showed that it's overlapping significantly for the Tropone reaction, but then in the hydrazone reaction, it overlaps very little. And that could be traced back to the degree of asynchronicity of the reaction. So in the Tropone reaction, you saw that the reaction was concerted and slightly asynchronous. So that means that both termini here will overlap quite efficiently. So you have a large overlap. And in the case of the hydrazone, when you have this reactant, the reaction becomes concerted and really asynchronous. So one bond forms way ahead of the other. And that is why this overlaps much less than this. And the less overlap of filled orbitals manifests in less Pauli repulsion and thus a faster reaction here. Again, we wanted to get a handle of the orbital interactions. And here we considered both the normal electron demand and the inverse electron demand. And in agreement with the seminal work of Wu and Albugen, we do see the HOMO activation, right? So here's Tropone's HOMO, and here's the HOMO of the hydrazone. The hydrazone is indeed, the HOMO is destabilized. That does lead to a smaller HOMO-LUMO gap, right? But it also leads to a poorer overlap. So that's one thing that is not really considered so often, is the overlap of these molecular orbitals. So the normal electron demand interaction does become a bit more stabilizing, but the inverse electron demand is way less stabilizing now. So the hydrazone has a much higher pi LUMO, and that really can't accept charge as much from the highest occupied molecular orbital of the malamide. So while benefiting from more stabilizing normal electron demand, it really is hurt by less stabilizing inverse electron demand interactions. Okay, it was very interesting to see after our paper was published in ChemCom. I saw this paper in the Journal of Physical Organic Chemistry, completely independent of our work. They arrived at the same conclusion as we did, using a completely different suite of tools. So they relied on quantum theory of atoms and molecules, and also a completely different decomposition scheme. So it shows that it is further evidence that supports our conclusion that the idea of asynchronicity is playing a major role in increasing the reaction rates of these ions when compared to Tropone. That was nice. So my final conclusion is that hydrazone ions along they catalyze Diels-Alder reactions by increasing the degree of asynchronicity, and that is the main reason why there is less Pauli repulsion between the reactants. And so we really challenged the explanation of Wu and Albugen that the enhanced reactivity goes by antiaromaticity gain. Eveline is not only an excellent scientist, but also a really talented artist, and she designed the cover of ChemCom. So I'm really proud of her for that. I just wanted to end with with making it clear that any of you can do this analysis too. I really wanted a clear and step-by-step sort of analogous to like a cookbook. I wanted an instruction guide that anyone can follow to do this activation, strain, and energy decomposition analysis. And that work was published in Nature Protocols in 2020. It's been really well cited, and it's a testament to its usefulness in facilitating these sorts of analyses. So please do dive in and check that out if you're interested. We summarized a lot of related work in a recent feature article in ChemCom, and all of the analysis that you showed, all of the graphs were all made using our open source software called PyFrag 2019. This was published in Journal of Computational Chemistry, and the activation strain analysis using PyFrag is compatible with not only ADF but also Gaussian, Orca, and Turbomole, and the EDA is compatible with ADF. That's what you've seen, and I'm really proud to advertise our team profile in Angewandte Chemie. Please check that out if you're interested to kind of know what the group stands for, our values, our views on education, and kind of how we exploit the synergy between all the PIs of the theochemistry group at the VU. The last thing to do is introduce the group and the funding sources. So this is our group. We're a beautiful, diverse a group of talented theoretical chemists, led by Matthias Bickelhaupt and Celia here. And Pascal is another PI in the group. That's myself. The money comes from NWO, also the VU. This is our Theochem logo here. And a really big shout out to SEM for all the amazing support over the years, and for access to ADF and all the amazing programs that under the hood of the AIMS driver. It's really incredible stuff. And Surf Sarah is our source of compute time. So thank you all, and I hope this was an interesting presentation.